10.5 Analysis Model. Rigid object under a net torque. The outline of this video is as follows. We will begin by introducing the rotational analog of Newton's second law, which connects the net torque on an object to its angular acceleration. To understand this relationship fully, we will first derive it for a single particle moving in a circle, and then extend that result to a system of particles that make up a rigid object. This process will lead us to define a critical new concept called the moment of inertia, which describes an object's resistance to changes in its rotational motion. We will then formalize these ideas into a powerful problem-solving framework, the analysis model for a rigid object under a net torque. Finally, we will apply this model to a classic example involving a wheel and a hanging mass to see how it all works in practice. In this section, we will establish the rotational analog to Newton's second law, which is the core principle of rotational dynamics. We know from our study of translational motion that a net force causes a linear acceleration, as described by the equation F equals m times a. The same logic applies to rotation. The rotational equivalent of force is called torque, and it causes a rotational or angular acceleration. The mathematical relationship is that the net torque, represented by the Greek letter tau, is equal to a quantity I times the angular acceleration, alpha. This new quantity, I, is called the moment of inertia. Think of it as the rotational version of mass. It is a measure of an object's resistance to changing its state of rotation. To develop this idea fully, we will first analyze a single particle and then generalize to a rigid object. The fundamental takeaway is this: net torque causes angular acceleration. Let us connect the tangential force acting on a particle to its resulting angular acceleration. This relationship is the rotational version of Newton's second law. We begin with the linear form of Newton's second law applied along the tangent of the circular path. The tangential net force, F sub t, equals the particle's mass, m, times its tangential acceleration, a sub t. Next we find the net torque about the center. Torque, represented by the Greek letter tau, is the product of this tangential force and the radius, r. Substituting for the force, we get that tau equals the quantity m times a sub t, all multiplied by r. To express this in rotational terms, we replace the tangential acceleration, a sub t, with its rotational equivalent, r times the angular acceleration, alpha. After substituting and rearranging the terms, the equation becomes tau equals the quantity m letter r squared, all multiplied by alpha. We define the quantity m letter r squared as the moment of inertia symbolized by I. For a single particle, it measures the resistance to being angularly accelerated. This leaves us with the essential result. The net torque on the particle is equal to its moment of inertia times its angular acceleration. Let us now extend our understanding of torque from a single particle to a complete, rigid object, like a spinning flywheel. This is important because it allows us to analyze the rotation of real-world, extended objects. We can model any rigid object as a collection of many small particles. Each particle has a mass, m sub I, and is at a specific distance, r sub I, from the axis of rotation. The torque on any one of these individual particles, tau sub I, is its distance from the axis times the tangential force on it. Using Newton's second law, this becomes r sub I times the quantity m sub I times a sub I. Now here is the key insight for a rigid body. While each particle has its own tangential acceleration, a sub I, they all share the exact same angular acceleration, alpha. The relationship is that a sub I equals r sub I times alpha. By substituting this in, we find the torque on a single particle is m sub I times r sub I squared times alpha. To find the total external torque on the entire object, we simply sum the torques from all the individual particles. The total torque on a rigid body is the sum of the torques on all the particles that compose it. We can now assemble these pieces to form the rotational analog of Newton's second law for a rigid object. This powerful relationship connects the net torque on an object to the angular acceleration it experiences. We begin with the expression for the net external torque. Because every particle in a rigid object shares the same angular acceleration, alpha, we can factor this common term out of the sum. The quantity remaining in the parentheses depends only on the object's mass and how that mass is distributed relative to the axis of rotation. We define this crucial property as the moment of inertia, symbolized by a capital I. The moment of inertia is calculated by summing the quantity m letter r squared for every particle in the object. Its standard units are kilograms times meters squared. By substituting I into our torque equation, we arrive at the fundamental equation for rotational dynamics. The net external torque equals I times alpha. This is the direct rotational counterpart to F equals ma. Torque is the cos A of angular acceleration, and the moment of inertia is the measure of an object's resistance to this change in rotation. The moment of inertia is a crucial concept that quantifies an object's resistance to changes in its rotational motion. Think of it as the rotational analog of mass. While mass measures resistance to linear acceleration, the moment of inertia, represented by the letter I, measures resistance to angular accelerations. However, unlike mass, which is an intrinsic property, an object's moment of inertia depends on two factors: its total mass and, more importantly, how that mass is distributed around the axis of rotation. For example, a solid disk is easier to spin than a thin hoop of the same mass and radius, because the hoop has all its mass concentrated farther from the axis. This leads to an important point. An object does not have a single, fixed moment of inertia. Its value changes depending on the chosen axis of rotation. The moment of inertia is always smallest when the object rotates about an axis that passes through its center of mass. This table provides the standard formulas for the moment of inertia for several common shapes, which saves us from having to perform a calculus-based calculation each time. These specific formulas apply to homogeneous objects, meaning they have uniform density, and for rotation around a specific axis of symmetry, which typically passes through the center of mass. Notice that all the formulas follow a pattern. The moment of inertia, I, is equal to a numerical factor times the total mass m, times a characteristic length squared, like letter r squared or L squared. This numerical factor depends on the shape and tells us how the mass is distributed. For example, a solid disk has a smaller moment of inertia than a hoop of the same mass and radius, because more of the disk's mass is closer to the center. Also, compare the two cases for the thin rod. Rotating the rod about its center is much easier than rotating it about its end, and the formulas reflect this. The moment of inertia is 4 times larger when the axis is at the end. The key takeaway is that an object's resistance to rotational acceleration depends crucially on how its mass is distributed relative to the axis of rotation. Let us apply our understanding of rotational dynamics to a practical problem involving an electric drill. This quiz asks how the stopping time changes when we use a bit with double the moment of inertia while keeping the initial angular speed and stopping torque the same. We begin with the rotational version of Newton's second law. The net torque, tau, equals the moment of inertia, I, times the angular acceleration, alpha. We also know that angular acceleration is the change in angular speed, delta omega, divided by the time interval, delta t. By substituting for alpha, we find that tau equals I times the quantity delta omega over delta t. To find the stopping time, we can algebraically rearrange this equation. This gives us that the time interval, delta t, equals the moment of inertia, I, multiplied by the change in angular speed, delta omega, all divided by the torque, tau. Since the problem states that both the torque and the change in angular speed are constant, the stopping time is directly proportional to the moment of inertia. Therefore, if the moment of inertia is doubled, the time required to come to rest must also double. Now let us apply our key rotational dynamics equation, torque equals I times alpha, to a classic physics problem involving a falling rod. We will consider a uniform rod of mass m and length L. It is attached to a frictionless pivot at one end, and we start by holding it in a horizontal position. When we release it from rest, gravity will cause it to rotate downwards around the pivot. Our goal is to determine two values at the very instant it is released. First, we want to find the initial angular acceleration of the entire rod, which we denote as alpha. Second, we need the initial translational acceleration of the free end of the rod, which we call a sub t. It is important to focus on the term initial, as the torque from gravity will change as the rod's angle changes, meaning the acceleration is not constant throughout the swing. This problem directly connects the concept of torque to the resulting angular and translational accelerations. Now we will solve for the initial acceleration of the rod by applying Newton's second law for rotation. First, we calculate the torque. The only force that creates a torque about the pivot is gravity, which acts at the center of mass, a distance of L over 2 from the end. This gives a torque of m times g times the quantity L over 2. Next, we need the moment of inertia for a rod pivoted about its end, which is 1/3 ml squared. With these two quantities, we can find the angular acceleration, alpha. We set the torque equal to I times alpha and solve for alpha, which gives 3 g's divided by 2 l's. Finally, we find the translational acceleration of the rod's free end. This is the tangential acceleration, a sub t, which equals r times alpha. Here, letter r is the full length L. This gives a tangential acceleration of 3 over 2 times g. The key result here is that the end of the rod initially accelerates downwards faster than an object in free fall. Let us explore a classic conceptual question. Why does a falling smokestack often break in mid-air before it hits the ground? The explanation comes from applying the idea of tangential acceleration to this rotating object. As the smokestack tips, it rotates about its base. While the entire structure has the same angular acceleration at any given moment, the tangential acceleration of each part depends on its distance from the pivot. According to the equation, a sub t equals r times alpha, points higher up have a larger radius letter r, and therefore a larger tangential acceleration. As the fall progresses, the angular acceleration increases. A point is reached where the tangential acceleration of the upper portions becomes greater than g, the acceleration due to gravity. For any part of the smokestack to accelerate downward faster than gravity alone would cause, it must be pulled down by the section immediately below it. This internal pulling is a type of stress known as a shear force. Ultimately, this internal shear force becomes greater than the structural strength of the smokestack's material, causing it to snap. Let us now apply our understanding of torque to a classic problem that connects rotational and linear motion. The setup involves a massive wheel, like a pulley, that can rotate freely on an axle. A light cord is wrapped around its rim, and an object of mass m is hanging from the end. When we release the system from rest, the object accelerates downward, and as the cord unwraps, the wheel rotates with an angular acceleration. Our goal is to find expressions for three quantities: the linear acceleration of the object, a, the angular acceleration of the wheel, alpha, and the tension in the cord, T. A key point to recognize is that the tension is not equal to the object's weight. mg. If it were, the net force would be 0, and the object would not accelerate. To find the unknowns, we must apply Newton's second law to both the linear motion of the mass and the rotational motion of the wheel. To solve this problem, we will apply our physics models to the wheel and the hanging mass to develop a system of equations. First, let us analyze the wheel as a rigid object under a net torque. The tension in the cord, T, creates a torque equal to T times the radius letter ARE. From Newton's second law for rotation, this net torque equals the moment of inertia, I, multiplied by the angular acceleration, alpha. This gives us our first equation. Next, we analyze the hanging mass as a particle under a net force. Two forces act on it: gravity, mg, pulling down, and tension, T, pulling up. We define the downward direction as positive. The net force is therefore mg minus T, which by Newton's second law equals the mass times its acceleration, a. This is our second equation. Finally, we must relate these two motions. Because the cord does not slip on the wheel, the translational acceleration of the mass, a, is directly linked to the angular acceleration of the wheel, alpha, by the equation letter A equals r times alpha. We now have three independent equations for our three unknowns: the acceleration a, the angular acceleration alpha, and the tension T. Now we will combine our three equations to solve for the system's acceleration. Our strategy is to eliminate the tension, T, and the angular acceleration, alpha, to find the translational acceleration, a. First, we use the torque equation and the no-slip condition to express tension in terms of a. From the torque equation, T equals I times alpha divided by ARE. Since alpha equals letter A divided by R, we can substitute to find that T equals the quantity I times A, all divided by letter R squared. Next, we substitute this expression for tension into the force equation for the falling mass, which was m times g minus T equals m times A. This is the key step, as it leaves us with a single equation where the only unknown is the acceleration, a. After rearranging the terms, we find our final expression, letter A equals g divided by the quantity 1 plus the fraction I over m, letter R squared. Notice that because the denominator is greater than 1, the acceleration is less than g. This is because some of the gravitational potential energy must be converted into rotational kinetic energy for the wheel, leaving less energy to accelerate the mass downward. Let us summarize the key ideas behind the analysis model for a rigid object under a net torque. This model is the rotational analog to Newton's second law. It establishes a direct link between the cause of a change in rotational motion, which is a net torque, and its effect, which is an angular acceleration. The central equation is that the sum of the external torques equals the moment of inertia, I, multiplied by the angular acceleration, alpha. The moment of inertia is the crucial proportionality constant in this relationship. It represents an object's resistance to being angularly accelerated, and it depends not just on the object's mass, but also on how that mass is distributed around the axis of rotation. The real power of this framework is that we can combine it with the particle under a net force model. This allows us to solve complex problems involving objects that are both translating and rotating. This slide presents two conceptual questions to help you apply the ideas of moment of inertia and torque. For the first question, consider a solid and a hollow sphere rolling down an incline. To determine which reaches the bottom first, think about how their initial potential energy is converted into both translational and rotational kinetic energy. The key difference is their moment of inertia. A hollow sphere has a larger moment of inertia than a solid sphere of the same mass and radius, meaning it is more resistant to spinning. The sphere that dedicates less energy to rotation will will have more energy available for translation and will therefore have a greater linear acceleration down the inclines. For the second question, we compare a hanging mass to a constant pulling force. In the original example, the hanging mass accelerates downwards. According to Newton's second law, this means the tension in the cord must be less than the weight, mg. The torque on the wheel is produced by this tension. In the new scenario, the cord is pulled with a constant force equal to mg. This new force is therefore greater than the tension was in the original case, which will produce a greater torque on the wheel.